welcome everybody to the fourth webinar of the online edition of the Protelec Electrostatic Conference. So I'm very happy to say that this initiative is obtaining a lot of success. I'm waiting you to subscribe to the YouTube channel in order to have a repository for future use and sharing of information about the community. Again, I would like to strongly encourage the youngest colleague to submit abstracts for flash talks. They can re-register in case they already did just for attending the presentations. And finally, I would like to mention that the next speaker next week will be Dr. Robert Krasny from University of Michigan. Now let's switch to the speaker of today. It's a very pleasure for me to have here Dr. Miguel Machuqueiro from University of Lisbon. So Miguel got his PhD in 2003. Then he has been working on computational structural biology and molecular modeling, and in particular with the development of new in silico methods to deal with pH effects in biomolecules. Then he continued his work and developed the stochastic constant pH molecular dynamics method. And then in 2009, he started his own group at University of Lisbon, extending the application of the constant pH molecular dynamics methodology to lipid bilayers, allowing the correct modeling of pH effect in membranes. And so Miguel today will be talking about the pH-dependent membrane crossing mechanism of Lewis-basis antitumor drugs. So Miguel, very welcome to be here, and you can start.
Okay, so hi to everybody, and I hope the share screen is working. Can you confirm, Walter? Yeah. So thanks, Walter, for the opportunity, the invitation, the opportunity for organizing these meetings. I think it's very nice way of dealing with the confinement and the social restrictions and the traveling restrictions. This is perfect. Every Wednesday becomes more interesting. The moment we are going to, we are having more of these webinars, and okay. My whole idea right from the beginning when I proposed to do something like this was to do some shorter presentation. So I was not, I had the chance to actually put two different projects and try to make it long, but then I decided, no, it defeats the purpose, and I would prefer just to spark the discussion right after. Because the idea behind what I'm going to present is just a very simple idea. It's something that is going around. Sometimes people throw it in discussions, but I've never seen something quantified the way I'm going to, I hope I'm going to convince you about the quantification, but at least this will be my, my basis in this presentation. So this is maybe because there's some people here in this webinar that don't know me so well and what I actually what I'm working with. So I usually have one or two slides just to highlight what we do. So it's probably not so different from what you are used to see, but we try to bring, of course, MD simulations of proteins to try to join together into binding. We are very interested in binding, what is happening, but from a, let's say, from a molecular dynamics perspective. When we look at a bind between donepezil and acetylcholinesterase, we are not so much interested in the specific energetics about it, how good affinity is. We are interested in the details, in the smaller details, and of course you will understand why in a minute. And was strong suit since well, while still I was working in Antonio Batista's lab, we were already looking at lipid membranes and lipid bilayers. So this the moment I moved this became the focus. The most almost all methods that we've been developing are always focused on interfacial membrane water, and of course what's happening at the lipid bilayer. And inevitably I ended up studying a lot of drug-like compounds interacting with membrane, and trying to understand how the physical properties of the membrane, biophysical properties of the membrane actually interfere with permeability and membrane crossing process. And one of these examples was, I promise I will not show you a lot of results regarding this flip peptide, even though it's my favorite. I tend to always put 1 or 2 slides of the flip peptide in my presentations, but the whole point is, of course, inevitably we will end up studying peptides across membranes, and as a test case for studying membrane proteins. That will be the end goal, and in some of projects we end up studying membrane proteins already, of course. Now, the glue that actually binds all of this, and the reason why we are in such a meeting, is because Antonio, he taught me how to deal with pH in systems like this. How can we actually introduce pH as a factor into the molecular dynamic simulations? And because after you learn how to deal with pH, it's kind of you cannot live without it, because now if I need to do something without using constant pH molecular dynamics, it feels I always feel short. I know I'm being a little bit nasty, but it's true. So all of these systems that are presented here actually ended up being focused on pH. So for this, we need to develop methods. Actually, the implementation of the stochastic method came out all from Antonio's head. I just tag along for the ride, and I learned how to implement this stuff. And I think now, after all these years, now I start to understand a little bit about the method. So it's a little bit like that. It slowly grows on you, and of course. The concept, conceptually, it's very simple. If you know how to do molecular dynamic simulations, if you know how to run Poisson-Boltzmann Monte Carlo to find the most, let's say, relevant protonation states of a given conformation, then we could actually make a cycle out of it, and with some technical detail on the relaxation side of the solvent. Technically, you could run a simulation where at certain intervals, you just ask if a group like the proton, and then the proton gets added or removed, and then you continue your simulation. So it's very, I will not go into details. If you want more details, invite Antonio, and he will give you a very long lecture on how all the details on this stuff. So maybe now, since we in the last 2 years developed or added this pH replica exchange formalism into the stochastic method, and since we did that, now we no longer have one of those problems that we start having when we have a very complex system. We start seeing something like this: some conformations that were typical of one pH were becoming very scarce, very difficult to sample on other pH values. Even though we know that they should appear, but because they're very rare, then the sampling issues start arising. And that's where replica exchange actually shines. And if we have, or my computer takes a little bit of time, we have to wait for it. So if we allow for replicas to exchange between pH values, then we can actually sample and allow for different conformations that would be like limited in their access to actually being sampled at all pH values. This is perfect to do when we want to do pH titration and get pKa values. This is probably one of the best way, because even though you can run replicates, what we have found is that it seems like the dispersion among replicates becomes smaller, even though we start very different different places from the conformational landscape, this got a very nice improvement in our pKa prediction abilities. Well, this is protein electrostatics, but because I'm here today, this is called protein and lipid electrostatics. And my computer is freezing, so I'm going to jump out of my membrane. I didn't like it so much. Well, but what is the focus of the project that I bring you here? The focus is related with tumor acidity. And we start looking at tumor acidity and why tumors are slightly more acidic than normal cells. We start looking at it from the FLIP project that I already showed you. Even in some protein electrostatic meetings, I showed you some results with this peptide where we can do some pKa calculations with it. But today I'm going to spend a little bit more time talking about tumor acidity because I'm going to address it from a slightly different angle. Well, tumor microenvironment is something that has been thrown since the 50s. Some people say that it exists. Some people say that it's very mild. But technically, you can actually, nowadays, there are techniques that you can measure because there are probes that can detect 0.1, 0.2 pH units. So they're very sensitive. So you can actually see at least the surroundings of the tumor, which we start already to be acidic. Of course, if you could do some kind of tumor perfusion, you could go inside more deeper into the tumor. Probably these pH values will be more like close to the 6 than it is to the 6.5 or 7. Sometimes the probes have difficulty. It's quite difficult to go inside solid tumors. Well, we know that this acidity is a kind of hallmark, not for all, but for almost all tumors that we have known. This is just an example of how you can map the pH on a human breast cancer tumor. Okay. I don't know if some of you still remember this. Others already read something about the FLIP peptide. This is this portion of the bacterial rhodopsin. That is a portion that has this ability of not having any structure. And when you actually add some liposomes, it has a very strong affinity for membrane, so it kind of sticks to the membrane. And then if you just acidify a little bit, and a little bit means coming below 6, then it folds into a beautiful helix. It's not as beautiful as this as this depiction here, but it folds into this folded and inserted state where we could actually sticks to the cells. And because it has this trigger around pH 6, allows for several groups to attach probes. I think I have some picture of it. If you attach a probe on the outside, the probe can be quite big, quite large, because it's not supposed to cross the probe across the lipid bilayer. So the probe can just stay on the N terminus of the peptide, so the outside portion, while the C terminus crosses to the other side, and then you have something like a hook into the membrane. So for this hook to actually be stable, you need to have pH slightly acidic. So this is how these guys, they developed this technology, and this is Don Engelman, Andreev, and Rezhesniak, the group in Rhode Island and in Yale in the US, where they actually added the probe, and by inserting a tumor in this poor mouse, where he had this tumor for 2 weeks growing on his leg. But then you can see a little bit of the kidneys, and you can see I can't remember the name of this organ, but and then you have the tumor. Well, if you get it in the right conditions, I went there to visit and I saw them doing this, and this is impressive. They can actually add the contrast enough to see the tumor, literally. And this technology is being used now already in some hospitals in the US, at least in New York. I know one hospital that is using this technology to direct the surgeon. The surgeon uses a special glass and he can see where the tumor is, which is at least for the initial reports was that it was amazing, because now they don't need to slice more than they actually need to remove the tumor. Well, this is when we start this FLIP project. I'm going to show you some one slide with results from FLIP, and it's very very fast. The whole concept of the peptide inserting, depending on pH, assumes automatically that you need how do you call it? You need at least one residue that is sensitive to pH, and the insertion is followed by the fluorescence spectrum of the tryptophan that is somewhere around here. It's not shown in the picture, but because the moment the peptide inserts, the tryptophan becomes more inserted, and then it gets a shift in its maximum absorbance, and then you can have a very nice titration. We call this the PK. I'm not calling it a pKa because it's not a pKa, it's a pK of insertion. So the pK of insertion is well known for FLIP, and it's 6.0, somewhere between 5.9 and 6.1. It depends on if the experiment is made on Monday or on Wednesday, because these are done by experimentalists. It makes sense. Every time someone different comes along, it gets a different number. And it's very tricky. It's a very nice system. But when we look at it from our standpoint, we need to compare this pK of insertion with something that we can calculate. And we can calculate pKa's, right? So we can run simulations of the FLIP peptide at different insertions, and we can calculate it. And of course, we can actually map the position of the key aspartate, where we right from the beginning, once we did the initial simulations, we realized that has to be this aspartate 14. So it has to be this aspartate residue that actually senses pH, even though a lot of anionic groups are on the C-terminus portion, that they will also need to protonate transiently so that the peptide crosses the membrane. But then on the other side, they might even be exposed to the water phase on the other side, or being completely in the middle of the membrane, and then it never sees pH. The guy that stands in the middle of the membrane, he doesn't know what is the value of pH because he never sees water. Okay, so if we continue titrating, at some point, the aspartate group will stop seeing water, stop having access to the buffer. The moment you stop having access to the buffer, then you don't titrate anymore. You stop exchanging protons. The moment you stop exchanging protons, the concept of pKa kind of breaks, or I don't know if it breaks the concept per se, but at least our ability to calculate the pKa, it doesn't happen anymore. We could continue to calculate the proton binding affinity and energy, just because we want to know how much would be the penalty to actually ionize this group here. But that energy does not really correlate as a pKa as we know it. So with this, we can actually do this small trick. Instead of having a pKa value, we can have a pKa profile. And some of you already seen this, or at least a variant of this graphic, and you might be like a little bit annoyed now. But I need to actually explain this, because I'm going to show you a lot of this stuff, and and this is really important to understand the final slides. So this is for FLIP, and because this is stuff that is submitted, so this is really new data. This is something that we did with the FLIP peptide in this last year. We built several membrane patches, different sizes, and the whole idea was, if we build it differently, will we get a different profile of peptide, of pK of the ASP14? And the thing is, the idea is, if we have an aspartate in water, which we plotted here on the top left side, if we have an aspartate in water, we would have something like 4. It's 3.94, something like that. So this is the pK of an aspartate in water. And then coming from here, now, of course, we don't have sampling for this region because the peptide doesn't go there very often. But if we bring it down, and at some point we start having some sampling. Of course, sampling here is terrible on this portion. That's why there's so much variability. Whenever we miss sampling, and the error bars will not help us, because our error bars are probably biased the way we start, and these are conformations probably from the start. Well, if we start from this, the first thing that we start measuring is the desolvation effect. And desolvation effect makes the pKa of aspartate increase. And of course, at some point, it will cross the phosphate region and enter the membrane. This gray area is the membrane, the inside of the membrane. 0 means insertion compared to the phosphates that are near the ASP14. So we calculate insertion by defining a plateau using only the near phosphates, because if we use all phosphates, then we are losing depressions and we start mixing things that are inserted with things that are not that inserted. But then our quite nice, interesting results were related with this region here. And this is the region where, if we think about it, the most strong interaction with phosphate are happening. And looking at our results, it's clear that we have a region that is not very good in terms of sampling, which is like -2 and -5. But then between -5, -6, everything converges into a value. And this is actually the experimental pK of insertion of FLIP, which is around 6.1. Of course, not everybody converges, because this 128 lipids, it's totally deformed and the membrane patch is too small, and we should never have built it. But okay, we wanted to have one that was wrong so that we can have more confidence on the other ones. So this is this was our results, and the punchline of this, after like 5 years of doing simulations of the FLIP peptide, we end up realizing that every time we were doing this a calculation, we were having a different profile, and we were so puzzled. Like, this is terrible in terms of. It's true. We were able, for most of the cases, we were able to reproduce the 6.0. This is the moment where there's like almost no water. So, and now we understand why, because there are interactions with phosphate groups that are very, very long, very persistent, and very, I would say, strong. And these interactions are the most difficult ones to actually converge, to get them right. And I think in some of these simulations, we have like 10 replicates. I would say that we'll need 100 so that this will start to converge. And but the good news is that even though there is some variability in this region, they end up all collapsing into this region here, which is the one that we wanted it anyway. So, but what is this story about the acidity? Well, I like this scheme because I will bring back this scheme in the end of my presentation with some biological insights. So, if we have to plot pH in a cell, in a normal cell, the pH outside is around 0.4. This will fluctuate plus minus 0.2, something like that, right? And inside is 0.2. It doesn't fluctuate that much, but it might fluctuate a little bit. But it's accepted that is around 7.2. 7.2, but it also depends on which kind of cells. There will be cells that will be slightly different, but okay, bear with me. This is just the normal cell. And then there's lysosomes. Lysosomes, everybody knows, this is like the trash bin of the cell. It's more than a trash bin, but it's also a trash bin. And pH is expected to be around 5, and when it's processing, when it's working hard, pH can be slightly lower. When you go into a tumor cell, what happens is, because of there's so much export of protons to the outside, this becomes slightly acidic. And this acidity that kind of, it's local. It's strange to be speaking about local pH, because pH is a macroscopic property, but you can actually think about it as proton availability, which will be higher in this region than further away from the cell. So if you move away from the tumor, really away, then this will end up going to a pH, a normal pH. But around near the membrane, you'll have some acidity, and this tumor microenvironment is the one that triggers the whole technology of FLIP. Inside, you have something more alkaline, more basic than normal cells, but it's just a small, but it creates a gradient that it's also interesting to explore. And it's also known that lysosomes will be slightly more acidic in tumors than they are in lysosomes. I don't know how much, but it's at least in the literature, this is people bring this up. Now comes the real key. If we have some anti-tumor drugs that actually have this kind of structure. The idea of plotting these 2D structures here is for you to have an idea that they are really different from each other. They are not really that similar, and because they have very different structures, they will have very different polarity, they will have very different pharmacokinetics. So this will be this will be important from what we are going to analyze. And the group that actually presented this data, the experimental group that presented this data for the first time in front of me, and I look at it and I started discussing this with the PI, is Yehuda Asaraf from Tech Iron in Israel. And when he was showing this, he was showing that how these compounds were being trapped inside lysosomes. So he was presenting it as a second method of drug resistance. So lysosome enlargement, lysosome overexpression, a lot of things related with lysosome, because he was convinced that these compounds were actually being trapped inside the lysosome. And he was bringing up the concept of Lewis bases, and because these Lewis bases get trapped in lysosome because they have a strong affinity for low pH. But he was not verbalizing the whole idea of what pH was actually doing and what's happening to these compounds when they are at the water membrane interface. And this is how the discussion started. And from here, when I start looking at these compounds and the Lewis bases, I realize, okay, sunitinib, okay, is an anti-tumor drug and has a pK of 8.5. And then I noticed nintedanib is the same, daunorubicin the same, and vincristine, of course, the same. So you see, all these pKa values these are amino groups. They are not acidic groups, just like the ones that I showed you in FLIP, where it was an aspartic acid. So now we have amino groups that have a pKa higher than 7. So for those of you that need a little bit of, are not so used and need a little bit of time to use this information, and because this is not obvious, what does this mean? Does this mean that how does the pKa will move with dissolvation, and what is the charge of these compounds in the different environments? So this is when my conversation started with Yehuda, and the whole idea was, okay, pKa is higher than 7. It means that when it's in solution, all of these compounds will be ionized, and it makes sense. All of these compounds will actually be ionized in solution, because with this pKa value, the protonated species will be actually the most stable. And if you look at the titration curve, you see that at pH 7 point something, you have 90 plus 95% of the compound will be protonated. And think about it. If we have to devise a new drug, you want it to be soluble. All of these compounds are very apolar. Their water solubility is very low. The trick is, if you make it a salt somehow, and Lewis bases are perfect for that, if you make a salt out of it, then these compounds will be soluble in water, and you can take it as a pill. Now, where does the disadvantage come from? If this compound is protonated, the protonated compound like this, even though they are very hydrophobic, this will have a huge barrier to cross membranes, right? Of course, from all this data that we've been looking, every time we have one of these compounds and we make it try to cross the membrane, doing constant pH molecular dynamics, the compound becomes neutral. And all our pK profiles also for the FLIP peptide assume that. So it's not difficult to figure or to think about this sunitinib to actually inserting into the membrane, losing the proton, and then becomes more lipophilic, and then it can cross to the other side. And maybe once it reaches the surface on the other side, it starts seeing water again. And then if it gains a proton, then maybe it's the extra push that helps the compound to actually leave the membrane again. So this transient deprotonation might be a trick that most of these compounds, and not only anti-tumor drugs, there are lots and lots of compounds that are have Lewis bases, and maybe this is actually the trick. Of course, we are not going to, at least for now, I'm not going to show you data of the full cross process, but we did constant pH molecular dynamics, and we can follow the compound at least until like the center of the membrane. Well, we can assume that it will not be that different if we continue to the other side, and we are exploring that. But if you think about here, and we can actually measure the insertion of this compound of the amino group. We can follow the amino group, which is the one that is sensing pH, and we can follow it, and we can see the insertion is not that different, and we can actually make calculations similar to the ones that I showed you to the flip peptide. Now, can we calculate the pK? Yes, but before I'm going to show you protonation. Protonation is more intuitive. So if we are in water phase here, we can actually, protonated is on the left side. So the scale is a little bit on the upside down. So if it's going to the left side, it means it's protonated. If it goes inside the membrane, you see it goes inside the membrane, then it becomes deprotonated, it becomes neutral. This is pH 8.5. So the compound doesn't have any problem to lose the charge so that it goes deeper into the membrane. Now, if you go into pH 7.5, it does the same, but it becomes a little bit more difficult, right? It requires a lot of desolvation so that the deprotonation actually triggers. And now the same happens for 6.5, and I have another one, it's 5.5. And it also happens, but you see, it starts to become tricky. It starts to become very, very difficult for the compound to actually loses the proton. It makes sense, this is energy. It makes sense. Now, on the right side, you have abundance. This is like this is unbiased simulation, so this constant pH molecular dynamics. So at pH 8.5, you see that the compound accumulates on the more interior part of the membrane because it's very, very happy and it's neutral. So it accumulates here. And of course, in the lower pH values, it's only very rarely it goes inside. And you see for the 5.5, the blue line here, we had trouble to have more points than this one, because at a certain point, the compound doesn't go inside, because the moment it loses the proton, it gains the proton again and it goes up. And here is the pK, because we have the data, different pH values, we can actually slice the system similarly and can calculate the pK value. And this is a very interesting result for sunitinib, because you can see that the pK 8.5 shifts a lot the moment the compound goes inside the membrane. And I have the same curve for vincristine, and you'll see that the pattern doesn't change that much. And we have this also the curve for nintedanib, which is much easier actually to deprotonate. And if you think about the tumor pH range, which is this one here, this shows that how deep you need to go for the population to change, gives you the energy, how difficult it is. So it seems that nintedanib will have a good permeability to go inside tumors, but for instance, vincristine will be terrible. Will be a compound that will have a lot of problems to actually go. We can actually discuss if at pH 7.5, if that problem will also is also present, yes, but let's look also at the pH of the lysosome. What this region here shows is that most of these compounds will have a huge trouble to get out of a lysosome the moment they fell inside the lysosome. The moment these compounds fell inside and they start seeing pH around 4 and 5, they would need to almost, look at it, they need to almost be at the middle of the bilayer, almost at the middle, to actually have enough desolvation strength to deprotonate and actually jump to the other side. And this is very rare, and it will be very difficult in terms of energetics. And this is also an example of showing 3 different compounds. I'm not showing the formulas of these compounds, but it's just for you to have an idea that these are central nervous system drugs that we take. I think one of these compounds is for the antidepressant. And some of them you might know also. And anti-something. They are anti-something. believe me. But these compounds also have Lewis bases, and we could parameterize the compounds, do the calculations, and you see the profile is there. And this also show, even though we don't have like a tumor acidity, unless the person has some brain tumor. This is a little bit dark, sorry. but technically, we are looking in this case for lysosomes, because it's known that many of these compounds, they become trapped into the lysosome, and that's why people take a huge dose, because the compound, the moment they go into the cell, before they reach their target, which is inside the cell, and very often it's in the nuclei, before they need to circumvent all this network of lysosomes. And if they fall inside one of these lysosomes, they cannot get out. That's why the efficiency of the treatment with this kind of Lewis-based drugs is not that efficient. So this is like a sum up of the whole concept. So if we have a compound that at normal pH is well distributed and has some neutral form, some protonated form, they can transiently deprotonate and get in a similar quantity inside. And then, of course, if they go inside the lysosome, they will get protonated and they'll never come out. In a new tumor microenvironment, the moment they reach the vicinity of the tumor and the tumor cell, their pool of protonated species is already higher compared with the neutral ones. So in terms of kinetics, this will already be slower, right? So you will have to wait until you have a deprotonation event so that it actually crosses to the other side. And then if these compounds get into lysosomes, they will have exactly the same problem as in the normal cell, with the disadvantage that in tumors, lysosomal overexpression up to a factor of 5 or 6. So tumors have 5 or 6 more times or times more these trash bins to actually remove. This is another process of resistance. So my argument here with these calculations is that besides the overexpression of exporters, which is called the #1 resistance of tumor cells, they overexpress exporters that act like pumps that are actually sending these compounds back to the outside. So this is #1, which has a lot of ramifications, and it's another story. But then overexpression of lysosomes, it's another one that is efficient against these specific kind of treatments. And I'm bringing up a third time, which is the tumor microenvironment, which actually per se, it's the first physical barrier, even before anything else. The first physical barrier is actually the acidity. So I'm a very nice guy discussing the problems. So what is the solution? How can we actually solve this? If we actually believe that there's a problem, can we solve it? Can we propose something to attenuate this effect? Well, yeah, ideally, if you can have a tyrosine kinase inhibitor that doesn't have a Lewis base, that would be preferable, right? Lewis base, but most of them have the Lewis base. That is the problem. And the Lewis base actually helps. I'm assuming. I still didn't do the calculation, but it might be helping to the binding, because this is the negative region here where sunitinib is binding to the inhibitor, to the protein, to the target. But ideally, we could devise a strategy where we change the Lewis base into something like the aspartate in FLIP, where it actually inverts the problem and gives an advantage instead of a disadvantage of having. You could have the charge, because a anionic group here would be negatively charged. It will transiently neutralize or protonate to become neutral to cross the membrane, just like the FLIP peptide does. And then once on the other side, it will not fall into the lysosome. If it falls into the lysosome, it will become much easier to get out. It's like immediately it will get out of the lysosome. So it looks like it's the perfect solution. The bad news is probably carboxylic acid. Here, it might not work. Carboxylic acid will have a pK that is too low. the energetic barrier just to cross the membrane is too high. Probably, I'm saying probably, because flip peptide has a lot of help by folding and getting extra energy by the folding process inside the membrane that drags the anionic groups and actually helps for the insertion. Here, the compound will not have that. They will only have some portion that is apolar. And okay, I don't have a solution for you, but of course we are working on it, but I would love to hear your suggestions. So in terms of most of the slides that were that I showed you were prepared by Tomas. That's why he has the right or the he has the embarrassment of having his picture shown, while all the others are, some of them are probably here and they are like this, like it's a good thing that I'm not appearing on the presentation. And I have to thank, the collaboration is with Yehuda and the funding from our National Science Foundation. And of course, thank you a lot to bear with me for this half an hour, 40 minutes. Thank you.
Thank you, Miguel. So we are ready for questions. Okay, I see Adrian is clapping.
Yeah.
So
hey everyone, sorry that I told Steve last week that I very intelligently have been setting a reminder to myself to attend this at 5 p.m. my time for the last 2 or 3 weeks until I realized that that was not right. Okay. Hi everyone. So Miguel, that was fantastic talk. Thank you. Let me ask you a question. A couple of them. So how do you deal with the dielectric in the membrane, right? So when you do, I presume you're doing, MD and then with Poisson-Boltzmann, right?
Yep, exactly.
So how do you switch from, essentially 80 to 4 or something, right?
Mm-hmm. Yeah. So the good thing about the stochastic method is that we actually, when we do it in proteins, we use the dielectric constant 2 for the protein. Here we extended that. So in our treatment, the good thing about the extension that I did to the method to deal with membranes, and we did it together, me and Antonio, while I was still in OERES, and the whole concept is that the membrane becomes the protein. Because this method was developed to allow lipids to titrate, imagine. So now we would have to allow lipids. My initial method, which I showed in 2010 in Telluride, while sleeping in Marilyn's couch, the first method was actually exactly that, very simple, where we just treat the membrane as another portion of the protein. So dielectric is 2. It might not. It's probably the whole idea of the different dielectric that you need once you treat the membrane as implicit, then it kind of is not present here anymore because you treat the membrane explicitly.
But when your peptide is, when your aspartic is outside the membrane in the water phase, right?
Water is 80, the membrane is 2.
So where, okay, so you're basically doing a PB with a boundary, right? Or
yes,
or you basically say, or you basically ask where is the aspartate, and then use a different dielectric depending on where is it. Is that what you do?
No. The aspartate belongs to the peptide, and the aspartate, the peptide, and the membrane, everything is 2. Only water is 80. Now imagine it's like my solute.
Yeah, okay.
My solute crosses the XY slab of the box. The XY.
No, that's okay. So you're using a PB method that allows you to have a horizontal boundary to define the solvent and the membrane, right?
No, Adrian. Let me try to help. I think what you do actually, you treat the membrane as explicit,
yes.
Right? And so
there's no implicit membrane.
Right, but he treats the membrane as explicit. That's why he doesn't need to define the boundary.
Yep.
He only needs to define the dielectric constant, like when you treat protein. system.
But you're not doing this thing where you have a step where you do a solvent relaxation.
I do, yeah.
Right?
I do. I need to do that, yes.
But
that's unrelated, right?
No, but when you do the Monte Carlo attempt, right? Is there a solvent or the membrane? Oh, okay, the membrane is there because you're treating that explicitly.
Always, all the energetics come from.
I got you. That makes sense.
The membrane is contributing to the background effect on the titration.
Okay, perfect. And then the question, I guess Marilyn wrote it in the chat, but I had the same question: is for peptides that have like arginines or something, there's been this discussion for a long time about,
for sure, yeah.
Are you bringing water with you through the membrane or not, right? Because if
we don't force arginine to go inside, they will never go inside. You have to force them in unrestrained molecular dynamics, right?
No, but but there's peptides with arginine that actually cross membranes, right? And the question, and what happens is there's always been this discussion if they deprotonate or if they actually essentially bring a bubble of water, a little bit of water with them, and then the effective dielectric is 80, right, or close, is high. So the question is
I don't know the physical answer to your question. I know what all the experiments I did with cationic compounds. Yeah. And if I don't allow them to deprotonate, they will bring a huge amount of water.
But what about your aspartic? That's your aspartic. Your aspartic could bring water.
It could, but it doesn't.
Okay, perfect.
So when you put your drug in the center of the membrane, does it have water with it? No.
So if
you make it so when you have the cationic, let's say you're at low pH, so you have the cationic drug. Does the cationic drug come into the membrane with bringing in the explicit MD? I presume you have explicit solvent MD.
Cationic drugs, they bring water.
They do bring water.
Yeah, they do bring water, yes.
And I think that's coming back in a sense so it's part of the PK shifts, the energy of moving the water in along with it, I presume. I mean, the other thing maybe when you're doing the PB calculation, if you are you removing that water?
All water disappears, yes.
Okay, so you're going to have a cavity there, and that's going to,
it's usually like 1-2 water molecules.
Yeah, no, but that's great. I mean, I would say that in fact, in my lab, we just, again, did another, new students put in MCCE and didn't remove the explicit water and then redid it with the implicit water. And you get really, really good agreement. I mean, it's not exact, but it's within a half a pH unit or less. So but so you are, again, coming back to Adrian's.
For sure. This region has some water.
Some salvation.
But this one has a little water, only a little.
Doesn't matter.
Most of,
you have two or three.
And most of these compounds
around the cation's gonna. If you took all the water and you did what Wei would do, or you did, you just made it 4 up into the boundary. You just did PK. Another few pH units. So that, I think that's great. I have no problem with that. It's nice if it's working. And it's not an infinite membrane. It's a finite membrane. So you will have waters coming in. They do, there's a little bit of salvation for them, even though it's angstroms away.
Yeah, I always associated this discussion that we're having now about like the cationic groups that actually bring more water as a salvation shell than the anionic ones. And it makes sense why most of these fusion peptides are actually cationic, because they are the ones that are able to stabilize, bring water, and then they need to assemble in a way to stabilize a pore. But almost all pore-forming compounds are cationic, as a rule of thumb. So we always, and something that I'm not showing is our most recent data is related with doing umbrella sampling and forcing the compound to actually reach regions that are like much deeper than -10. So we can actually go to -18. And the thing is, at some pH values, when we do the calculation around like pH 4 or 5, we are not able to deprotonate. It actually makes a ripple in the membrane. Right. But the good thing is that we went to use umbrella sampling and then use those umbrellas to actually calculate the permeability using the ISTM method. And the thing is, this makes terrible membrane permeability, which is actually what we want. Even though we might be off by 1 order of magnitude, the whole concept that the membrane permeability depends a lot on the pH. Then that's the whole point. That's what we are actually trying to show you here, is that if you lower pH, compounds will have trouble crossing. Makes sense? That's the punchline of my presentation. It would be much nicer to show it with umbrella sampling and then membrane permeability calculations that we are running now.
Yeah,
that's for next year.
Yeah, I want to make a comment on this. Right, indeed, actually, the membrane permeation simulation from sampling point of view is very difficult. It's generally considered as unsolved problem, particularly for charge systems, right? And so I wouldn't use MD, whatever you observe from whatever MD simulation trajectory, and then to say that's the fact, right? And so because actually the charge, even
it's
the
very difficult to converge. Completely agree with you.
Yeah, not even converge. Even you get the correct membrane structure, correct membrane deformation, and then correct the water pore formation.
Yes,
and then that's
you are completely right.
And so the usually in general right now the norm in the field is actually we usually don't trust, right, unless there's experimental data, we don't trust actually whatever we claim, right, for the membrane permeation data, right, and sampling data.
I'll need to comment on you because there's an asterisk on. I'm agreeing with you. You are completely correct, but if we run the calculation, the number that comes out might be 2 or 3 orders of magnitude away from the experimental number. We are assuming equilibrium because we are using a method to actually integrate all the windows of the umbrella sampling or any other method that does this. And in the end, we have a number that might be off like 3 orders of magnitude. The good thing about what we have here is that because we can do the calculations at different values of pH, it kind of, a lot of the error gets canceled out because we are comparing just how the energetics due to the larger population of ionized compound. You see, this way we can cancel out a little bit, not all, and you have to put a grain of salt in it, but yeah.
Yeah, I understand your argument. This is the same argument people made 10 years ago. I know Martin was involved in that, right? That's the time actually. So I have to bring the history back a little bit when what's the name again? When Bertram Garcia Moreno made this experiment, right? And that time actually very interesting observation was actually when people use implicit solvent model to make assessment on pKa. Even for these, it's very easy to get correct answer even for the so-called buried residues, right? Even that there's no, afterwards we all know this buried residue indeed actually need involved in the coupling, right? Even that time we didn't see the coupling when you use GB model, PB model, you still get correct pKa. And the reason actually, I think actually after 10 years, if you look back, the reason actually the pK was right is mostly because actually, implicit solvent model, you said there's a cavity, right? Even there's no sufficient volume for water, right? You still assign the cavity, you still give a direct constant which is not equal to 1, and they will help reduce quite a bit of the help to stabilize the charge state quite a bit. And so I want to just right now come back to your comment, right? And I wouldn't use the fact that we can get the correct pKa as evidence, the structure you observe is right. It's all we all know actually that the deformation is a very long time scale event, right? That time scale even know actually from measurement now actually there are a lot of measurement now going on in like Oak Ridge National Laboratory. That time scale is so slow, too slow. It's go beyond actually regular MD sampling time scale, right? And so for instance actually when you have a membrane system, you create a lot of cavity of this lipid, right? This cavity when you use PB or GB, you're gonna assign the cavity. And that artificial cavity will definitely stabilize, will lower the pKa. Will not lower, will stabilize your charge state, but depending which way you go, and artificially.
I'm going to say, I mean, it's kind of funny to argue that we got terrible results rather than good results, but when things have real changes in structure, continuum is inappropriate, and we don't get good results. And with Bertrand's stuff, I mean, we got reasonable results, but with a pretty high dielectric constant that is essentially saying that we are missing a lot of conformation changing.
Well,
so, it's...
But I don't think this membrane insertion problem is the same kind of problem as the ones from Bertrand, because
I agree.
It's another level. No method like this will ever get it right for those PKs. You need to compromise. You need to model the two stages. Is a two stage with a very slow transition. So you need some special method to get exactly right, or you get it right doing some linear interpolation out of it, and you might get lucky. That's what some people get lucky.
So in that regard, it's the same, right? Bertrand system is the same thing. You have a conformational transition. In this case, you have membrane deformation, right? And then so Bertrand system, you have water, and then so the solvation into the water entering. This is the similar thing. Sampling wise, the nature is similar.
Well, I would disagree, and because I throw away one portion. I'm not comparing the pKa, the macroscopic pKa of one of these compounds with, how do you say, if I do the calculation in water, I get the water pKa of all of these compounds, but I have no information about what will be the pKa of these compounds in POPC liposomes. I have zero, because I don't have a macroscopic value, and I don't care. I don't care. What I want to do is to calculate the proton binding affinity. It's an energy. I calculate the proton binding affinity along the insertion. It's slightly different because here I have sampling along the insertion, something that I don't have with the Garcia Moreno simulation. Because if I start on this state, I stay on this state forever. If I go into the other state, I stay there forever. I don't see the transition, so it's like a 4-state when I wanted to have a 2-state calculation. Here I'm grasping dissolution mostly. Here there's not even other groups titrating, so I'm just end up having majorly the dissolution effect on these cationic groups. And I think this method captures them. And even though it might be 1 or 2 waters coming down, they might be missing out in the Poisson-Boltzmann calculation. They might not be being introduced, and there's no cavity because the probe of Delphi, it actually will never make a kind of a vacuum inside this. It will make one single probe around the protein, and now my membrane is my protein to define the inside and outside. And it's not facing solvent. If it's not facing solvent and it's not large enough, I don't think this one or 2 water molecules will have an effect.
I'll bet you do. You should be able to look at an EPS, a map for where the dielectric constant is inside.
For this system, I didn't look at it, Marilyn, but I looked at other ones when there was like 1 or 2 waters.
Yeah, they don't need to be contiguous with the solvent outside. At least in Delphi. I don't know.
Yeah, but you need to be large enough to actually. Yeah. Completely right. Yeah.
There is a question from Thomas Lauer. The old protein chemist would point out that proton binding may be accompanied by concomitant anion binding. That is, there is no net change in the protein peptide charge. Do any of that simulation or models include this fact?
No, they don't. Yeah, you're right. It might be possible to actually have something canceling out the charge, like some anion coming in. To be honest, this is something that has been puzzling me. I've never done any calculations relating to that. I don't think it would be that difficult, I think. But some in literature, I've seen some anion kind of balancing the charge, coming in an ion, and this is the part that puzzles me because my mind cannot grasp the idea of these 2 let's say ionized species being able to stabilize each other in a way that it will make the membrane permeability improve. If you use something like some acetate to actually stabilize, maybe one small organic molecule, organic acid might be, and you might get it stabilized. I don't know. That is something that I would love to explore, really. But like a chloride, that, I don't know. Chlorides, they just hate membranes.
Okay, there is a further comment from Marilyn. You could look at the sole dependency in PB, that is the bifocal ions. Does the molecular dynamics have explicit ions?
In these simulations, they don't. That's the beauty about our method, is because we still use reaction field. We don't need to balance out charges, and that is a great advantage compared to many other methods, as you all know. And we don't need to add ions to our simulation. Most people, they add ions because they have to, because most of the ions, they just stay outside. And if the ions stick too much to the bilayer, it means that probably they are wrongly parameterized, which is also common, by the way.
Okay. There is a reply from Thomas, who says the binding constant for chlorine is of the order of millimolar. The binding site is the amide proton.
I didn't get it, sorry.
The binding constant for chlorine is of the order of the millimolar, while the binding site is the amide proton. So a chlorine might bind to the amide proton.
To the amide proton? Where is the amide proton?
And not the side chain, it says. You
mean here?
Your drug, I think.
On my drug, the chlorine will bind here.
Yeah.
Well, I have no idea. No, I have no. I will have to do some maybe some QM calculations to try to find which will be the most stabilizing conformation for chlorine. Yes, that would be. Possibly. I don't think it would be. It would not be complicated. Yeah. And this is almost as more. Even though this has a +1 charge, this is actually, if you look at the dipole, the directionality, this dipole might be stronger. So yeah, it makes sense. It might be true, but I have no idea to know.
The problem is in the initial state of the model. I mean, the reply from Thomas.
The initial state?
Maybe
is Thomas still here?
Yeah.
Talk to me, Thomas.
When you set up the neutral boundary. I'm reading the chat.
I'm not reading the chat because I'm sharing the screen. I'm sorry.
Can you hear me?
Oh, yeah?
Yes.
Okay. I'm sorry. The problem comes with a lot of the simulations. When the box is built, it is made neutral by adding salt, by adding counterions of some sort. If you don't count those counterions, those initial counterions properly, you're going to have a problem. If you assume that your protein or your peptide is only binding protons, you're going to set up the wrong initial state. You have to include the fact that proteins combine significant quantities of anions and cations, but primarily anions, to the initial state.
It's true.
Thanks.
Yeah.
I enjoyed your talk very much.
Oh, thanks. So I agree with you. It's completely true. But it's one of those approximations that we are doing. We are just allowing for protons to bind. And because they are the most interesting when we are dealing with pH, but this is just one of those approximations. Another one will be, for instance, I always mention this kinetics. So what is the rate? And Adrian is here, Antonio is here. So they also do the same. What is the rate by which we actually test and check if a group would like to have a proton there or not? Because protons are not explicit, they are implicit in a proton bath, let's call it like this. So what is the frequency? And this frequency can be tricky because, well, none of these frequencies that we all use, and when I say all, I really mean all of us, none of these frequencies are realistic, right? Of course, the frequency will depend on pH because it depends on availability of protons, but this is all the frequency that we do the testing is probably typical of a so low pH that everything is flooded with protons. And this is not very realistic. But we need to it. We need to do that. Otherwise, we will not have enough sampling.
So my point is, Miguel, since you, the frequency at which you try to attempt this, so there's two parts, right? If you want to do kinetics, then you need to do it every millisecond, right?
Yeah,
that's the natural time scale.
It depends on pH. It depends on pH.
Yeah, but even right, but that's right. But it's way longer than anything we use, right? But but if you're looking at equilibrium, in principle, it shouldn't matter, right? I mean, it should matter. How often you try a Monte Carlo step is irrelevant.
It's just that you are trying one conformation that is very similar to the one that you tried 100.
Well, but that's essentially what you're doing is you're wasting time. But it cannot be wrong, right? It cannot make the simulation wrong.
Well, yeah. In terms of equilibrium, I agree.
Right.
Yeah.
Right.
Otherwise, we'll be out of business.
Right. Exactly.
I think there was a raised hand from Stefan Hansen sometime before the. Do you still have a question?
No, that discussion has already been taken by or initiated, so I'm very pleased.
Okay. Okay.
It's late in Europe.
May I ask a question?
Yeah, Antonio.
Of course.
Go ahead.
It depends.
Well, it's more of a comment, maybe. It's related with what you and Adrian were just discussing. Because I mean, when we talk about sometimes there is this, I wouldn't say confusion, but we tend to forget that when we are doing simulation, we are really not expected to get the kinetics right. Mm-hmm. We are just sampling in terms of an ensemble, and that is particularly obvious in the case of constant pH MD. Mm-hmm. But even in normal simulations, unless you are doing a constant energy simulation, you are not really sampling kinetics strictly. I mean, even the simple fact of using a temperature bath, it means that you are fiddling with the Newton's equations of motion. So, I mean, we are really sampling in terms of ensemble. So,
can I disagree with that?
Go ahead. Yeah.
Since this is the proper forum, right? So, for the constant pH, absolutely, completely agree, right? Yeah. But if I do a regular MD of a protein and I see a side chain flipping back and forth, right, between two states, mm-hmm. I'm not saying the force fields are any good for this purpose, okay? But in principle, I should be able to get the rate if the force field is correct. Yeah, just by the number of switch per unit time.
Yeah, it's just that the force fields were not parameterized for that.
No, that's okay. But that's a question of the force field, not of the fact that you're sampling MD, right?
But Adrian, would you still believe this? Regardless of the thermostat you are using?
Yeah. We check that for a number of things. Yes, I mean you have to be careful. You don't use Berensen, right? But
of course.
No, I love this discussion. Adrian knows actually I love theoretical discussion. By the way, Antonio, I haven't seen you for years. Nice to see you. And so on this discussion, actually. Number one, I think in principle, strictly speaking, what Antonio mentioned is correct, right? When you do so-called current ensemble MD, and your thermostat influence energy flow pathway, you influence kinetics, right? Yeah. So in practice, in practice for long-time skilled event, because actually the most time actually when you apply the general ensemble, not general ensemble, the current ensemble MD, the thermostat is pretty weak reservoir, right? And so that does not influence long-time skill dynamics, right? So the event you see for the long-time skill process still, at least actually the kinetics still hold in a certain way, right? And so I think impersonally that's true, right? And so when you apply the uniform thermostat, like particular long-run thermostat, you really alter the energy flow pathway, and so your kinetics really altered, right? But the long-time skill event, because you lose memory, so that you still recover the long-time skill kinetics. And so that's what Adrian mentioned, this pragmatic view.
Yeah, but the point of my comment was I kind of didn't finish it because then
sorry.
But it's okay. It's good that you jumped in. Because my point is, for instance, in the thermostat, you have parameters that you can tune to get the right kinetics, right? You can change the math, so-called math of the temperature piston. Let's call it this way, for simplifying. And here you could do the same. I mean, you just don't do it because otherwise you wouldn't get any sampling. You could switch the protonation frequencies to very slow very slow value. I mean, just try to flip proton once every, I don't know, microsecond or something like that. Yeah. That would be more realistic. But then, I mean, you wouldn't have any sampling. So the difference is that in the other cases, you can have the luxury of tuning your adjustable parameter to a value that gives you the proper kinetics. Here we don't have that luxury, because if we
That's right.
we completely lose sampling. So sampling would be terrible. That's my point. You see,
I agree.
Yeah, if it would be difficult to have kinetics with the force fields that were not parameterized to actually get good results, because most of them weren't. But even if we had that, the moment we start doing constant pH molecular dynamics, because of this simple necessity, we stop having that, because we are promoting a change in protonation. For those of you that I don't know if you're understanding, but if the moment you start changing protonation of a given side chain, the kinetics gets completely wrong, and it will depend on the rate by which we are actually changing the protonation state. So everything gets, and then it's not one, it's all residues that are titrating, that the whole kinetic part of the simulation becomes like that.
And some of the residues may be titrating at quite different rates because of the environment where they are at. Mm-hmm. Some of the titrating sites could be slow, and some could be rapid, could be fast. So in principle, there is no reason that they should be all flipping with the same frequency.
Yeah.
And in some cases, in terms of sampling, it might even be advantageous to have a slightly slower rate, at least for some of the sites. What I mean is, for me, it's not completely obvious that you want to flip as fast as possible. Because that would depend. I mean, if you think about these really old simulations with Lennard-Jones liquids, with some Monte Carlo simulations, the optimal way of sampling space was not with the faster.
No, but but again, per unit what? That's what's so. My point was basically that if you try to attempt whatever Monte Carlo you want to do, every single step, if you follow the mathematics and your program is correct, there's nothing wrong with it. You're going to be wasting a hell of a lot of computer time.
Yeah.
And your exchange could be awful or small, or it doesn't matter. So there is, for a given problem, there is some attempt frequency, if you want to call it, that gives you the acceptance ratio that gives you best computational effort, right?
Right.
But that's different from the.
Oh, we lost.
You froze, Adrian. We lost you.
But he was very convincing.
Got you again. Okay, you're on again.
I'm on again. What I'm saying is that again, from a pure formal point of view, try every step. Who cares? It should be fine. You're going to be wasting a hell of cycles.
Mm-hmm.
So when we talk about an optimal trial or whatever, it's to sample more per unit computer time, right?
Mm-hmm. Yeah.
And that's okay. That's perfect. That's it. Yeah.
Yeah. No, actually, I think Antonio's point. Actually, I agree with Antonio's point. This is come to the deep part of sampling issue. Sampling issue is about this, right? You have multiple variables, you have multiple degrees of freedom. They co-evolve at the same time, right? And so when they co-evolve at the same time, right? And so you have to care about so-called, we call it environment activation relaxation, right? And a different part need to have a very good. It's not like we try every single moment to the best, right? If you try every single moment, you generate so-called high frequency transition. These usually they can hurt, right? And so from sampling point of view, right? I think Antonio's point is well taken. I agree with you. This is something I've been considering for a long time too.
Might get trapped into something in between, and you don't allow the system to have time to actually transition.
Yeah, exactly. And so
because you are creating.
I
keep coming
sorry,
back.
Right. No, actually, I completely disagree with that. It's sorry.
I remember.
Let's do this. Let's do this. Let's do everything in Monte Carlo. Let's not do MD. So again, I'm okay. Wait. I'm such an atheist that I don't even use that name because I don't acknowledge. I don't want to call myself no theist, right? But I believe in the God of Monte Carlo. You ask Monte Carlo a question. Monte Carlo answers is the oracle. It can give you two answers, yes or no. If it gives you yes, you cannot be wrong ever. It's impossible to be wrong.
On the
you might waste in computer time, but the sampling has to be correct.
Adrian, we are not talking about wrong or right. We are talking about what's the most efficient way to sample.
Absolutely, efficiency, absolutely. Efficiency, yeah. I completely agree with you.
Yeah.
I don't know if you're agreeing by the right reasons, but well.
But I think actually, this discussion is so interesting. I really want to bring one important point, right? I think actually there's a paper, even actually the speaker's citations, to me actually is not right, because I think Antonio's first paper was published in 1997, right?
The
first method, yeah.
Well, there were two methods. The first one is from 97, and we never used it again.
Okay, I see.
So it's from 2002.
Yeah.
And so this is so-called hybrid nowadays, including agents using, including the Charlie Bruce using, of course, I had to use lambda dynamics. The hybrid means actually you propagate the dynamic using explicit solvent, but actually you use actually the implicit solvent to do Monte Carlo, or you propagate lambda dynamics.
Yeah, that has some problems, right?
No. I think this paper was really traced back to Antonio's work. That's Antonio was
right.
Right. So the only thing actually, there's another comment on this. Actually, it's good work, but I think that there should be some concern, right? When you do the simulation, you need to measure your average kinetic energy constantly to make sure, because actually this is so-called non-Hamiltonian system. When you have non-Hamiltonian system, you need to really monitor your average kinetic energy to make sure the temperature, the structural temperature, will not be way off from the reservoir temperature, right?
Sure. Yeah.
This felt a little bit like some Telluride discussion, right, Marilyn?
Well,
I like it.
Yeah.
That was the intention.
The main difference is that we didn't stop you at your first slide.
That's true. You are becoming too polite.
Zoom is a different medium. We're learning to be blunt, and one of the things I was thinking about is with your sofa story is our friend Tom Haynes, because there's the thermodynamic side, we're getting the number right, but then also the way that the proton gets into your guy in the middle of the membrane, and that's almost and we think about that because we're thinking a lot about proton transfer these days. Is
a lot of this
started with Tom Haynes. You probably get a water wire that's developing that's going to move the protons in and out. And so whether you see transient water wires, that's going to talk about not the PK, but the mechanism.
Yeah.
Yeah, I agree, Marilyn.
Yeah.
Hi. Hi, everyone.
Hello, Anna.
Hey.
Yeah, I had to switch off at some point because of a meeting, but yeah, so, and you could do explicit solvent MD also, just with a fixed protonation state, to look into that as well. That might be, and also
Yeah.
like ion binding, possible ion binding somewhere.
Yeah, what we see visually is that whenever you stabilize, or if you observe some segment where there's a lot of protonation, ionization on these compounds, or deprotonation on the aspartic ones, you actually see some. Well, it makes sense. Like, you are generating a charge, and for a certain period of time, you are doing MD with the charge in there with nothing to stabilize. So you are kind of promoting some rearrangement in the water wire being formed to stabilize the charge. It might be turning things upside down. It should have been the water promoting actually the ionization event. I don't know. Is the egg or chicken? But we observe exactly what Marilyn was describing, really.
I think these are interesting to look at for their own right, because they do, you know, make leaks in the membrane. They also are important for, you know, for proton pumping, you know, how, you know, so anyway, it's a nice side issue. And it's probably more on the, might be more on the time scale at which your molecular dynamics is real. Tom Haynes
would be, if you would be here, you would say that, yeah, now you have to run the calculations with some like cholesterol or some esterol, so that it then I assure you that everything will change, because everything compresses and the membrane will not leak anymore. So this is all the stuff that I learned from Tom.
I will pass this on to him. You know, we still speak on occasion. And they're doing, he and his wife are both doing well. So, but yeah, no, I think that's, the lipid point of view is actually quite interesting. And
one day this meeting will be protein and lipid electrostatics.
Hey, you agree, you
no pressure.
Walter, and I'm sure he would have no, we also don't have any nucleic acids, you know, we've been talking, you know, Bertrand has been talking about bringing nucleic acids in. So, you know.
Shall we move to bioelectrostatics?
Almost.
Biomolecular.
So.
Biomolecular electrostatics.
Okay. So, does anybody else have any comment? So then let me thank Miguel for this very nice talk, and that brought to this exciting discussion. And thank you everybody else for waiting here, for participating to the discussion. So let's meet next week with Robert Krasny. Okay, thank you.
See you then.
Bye bye.
Nice seeing everybody.
Bye bye.
See you.
Bye.
Bye bye.